There are two things that functions have to do in a functional programming language to enable all those nasty tricks. This being first class and pure. How does Rust achieve that? So first class function is a function that can be created on demand, somewhere in the code, be stored in a variable, passed as an argument to a function, and returned from a function. So can you read this code? Is it big enough? Bugs in the back? Yeah, OK. I can't, I need to get closer. So this is a very, very simple function. It just takes an argument called x and adds 5 to it. It's actually closure, not a function, but for the sake of this talk, this will do. And I can store it in a variable called add5. Rust doesn't makes me type or type annotations, pun intended. But these are strong typed closures. I cannot take another closure and or pass it to a function that requires a closure, a function with 2 arguments. Only one, and probably this code compiles to integer, compiles to a function or closure that requires an integer argument. And actually, I can force it to be a 32-bit integer by requiring it to return it. Type inference in Rust is on par with what Haskell type inference can do. It can deduce the types and fill all those nasty details so that I don't have to worry about it. So yeah, I created the function and stored it and called it. All great. So I can also write a function that returns a function. This box thing, for those who don't know Rust, is tells the compiler basically to allocate this on heap, not on stack, which matters in Rust. And this piece of code does basically the same that inlining the closure did in the previous slide. It creates these other functions create another function and returns it on a heap, so it can be referenced somewhere else. And actually, Rust compiler is smart enough to understand that this is a function which will be called somewhere, and I told it to allocate it on the heap, but depending on the context I use it in, it probably optimizes out the allocation. So this will cost me nothing in terms of performance. And actually, I learned yesterday that there is very little nice piece of syntax in nightly Rust that says just don't bother with the box thing. We will do it for you. Nightly Rust. Rust has 2 release channels: stable, which is stable, and nightly, which is for experiments and things that need to sometimes to be tested on different contexts before they become stable. So yeah, I got a function that returns a function. So I can have a function that takes a function as an argument. The applied to a function is very basic, takes an integer and a function that requires an integer and applies one to another. And can take my other function, output of the other function I defined previously, or take ad hoc closure defined just what I needed. So yeah, functions that can be created on demand, check. Stored in a variable, check. Pass as arguments, check. Return from functions, check. Cool. How about purity? Haskell is a great example of language of pure functions, and Rust cannot compare to that. But closure is, as we said, that they have functions that are pure. That means they operate on immutable data and have no side effects. It's not true in closure, but in general, they do not do nasty things with data, don't change their values when you're not looking. And I can do something that's simple, but it's actually cheating. You can define pure function like that in C as well. So let's do something else. A struct is something like an object in Rust. So you have a piece of memory that consists of two integers. Integers? Yes. And we have something that operates on it, a method. It is a way to define methods in Rust. And looking at the type signature of this function, you can pretty much guess what it's supposed to do. It takes self and the number and another number and retains another point. It's called move by, so you can pretty much guess what will be inside that function. But look at this one. It's almost the same, but takes save as a mute or mutable reference. That means this function is supposed to change the object itself. The object is called upon. So you can pretty much guess what this should be doing. And of course, when the first function we cannot modify self is to return something new. Like returns a new point with those fields x and y increased by respective integers, and the other one mutates things in place. And if you ever make a mistake and forget the mute thing, the compiler will just say, no, you cannot do this. This is pretty basic. And this way, when you have something, some piece of code, and you look in type signatures, you just see that things that can change and see that things that guaranteed not to change ever. That is not true. I told you. You can, of course, change things. Like you can insert the print statement and change the so-called world around your code. And you can do all kind of things like open files, open connections, talk to databases, try to whatever modify some memory. Unless you don't change the values passed the function, the compiler will not complain. So it's not pure, but it's pure as long as only talking about the parameters of the function. So you may be asking questions, okay, if I can open a connection, maybe I can store something in some global state, global variable, and introduce some kind of change there. And you can certainly do that. This is a way to implement a static global variable in Rust, and you can, of course, say it's a mutable variable, and you can try to change it. But Rust would say, are you really sure you should do that? If it's not a mistake, mark it. So Rust would require to surround this piece of code with unsafe keyword, which means that this is a way to tell compiler, do not worry, I know what I'm doing, trust me, this will be all right. And anybody looking at your code later will say, aha, unsafe, I should be worried about that. So functions in Rust are pure enough for all practical purposes. And because it's a systems programming language to do all nasty stuff with hardware and low-level things, it lets you escape this purity and do what you want, basically. Okay, functions. C has functions, and C pretty much can do most of that. You can store a function, you can pass a function, you cannot create in runtime, but most of that you can do. How about something else? How about data types? I've mentioned that Rust is a strongly typed language. It has type inference. So we'd expect that a modern type system will allow you to do very nice things, like implement algebraic data types. So examples in this section will be taken basically from Learn US Haskell and translated to Rust. So this is the simplest algebraic data type you can have. It's an enum, just like in C, which has two values, and you can use them in a variable. But this is, again, cheating. Any language can do that. Most of the languages can do that. So this is something more complicated. We have the shape type, which can have two values, circle and rectangle. and circle requires you to use 3 floating points numbers, and rectangle expects you to use 4. And you can again use this syntax in the last line to create a circle. If you have in scope something else which uses also the name circle, you will be required to use the qualifier shape colon colon to disambiguate it. So yeah, this is how you use it in real code. It's not as elegant as in Haskell or Scala, but you can match against the value, and if it's enum, it must be the match must be exhaustive. If you forget something, the compiler will say that this will not do. And you have all those nice things in you should expect from a modern programming language, like destructing, like ignored parameters. This function, because it just takes a reference to shape, will not modify shape, of course, and you can be pretty sure it won't. But this one thing, having things like circles and rectangles and maybe other shapes, can we have something more generic? A type that can hold any type, just like maybe in Haskell, which is hold any kind of value. And sure enough, Rust have an option type, which is so-called generic type. We can hold nothing or none and some value of the shape of the t. And you can use it, and the type inference, and the compiler will know which type is actually used. Option of strings, option of ints, anything that can be expressed in type system can do. But we like to, sometimes we'd like to have some restriction on the type. Like this is not a enum, it's a struct again, which have 3 type variables, each of the fields of different type, and we can just create it in line, just putting values to the constructor of the object of the struct, and have Rust figure out what to do with that. However, if you would like to have something, it just prints not that nice if you use the default things. You might want to say, okay, I know better how to print this thing to a string, or to format it to string to show it. This requires you to use some restrictions. Not everything can be printed to a string, right? You cannot print a function to a string. You cannot print a closure to a string. So this is not true that any value can be substituted for this t, s, and v type variables. And as any mature programming language, Rust allows you to specify that there are some restrictions to those types. And in this case, all of those need to have a display trait, which will inform the compiler that those types need to know how to display themselves to a string. Pretty basic stuff, if you think about it. Which brings me to my next topic, traits. Traits in Rust look a little like type classes in other languages. A trait, quoting the Rust book, because there's only one at the moment, is a trait. Trait is a language feature that tells the Rust compiler about functionality a type must provide. Well, a type class is a sort of interface that defines some behavior. You can say that it's pretty much the same thing. And let's see how it works. This is Haskell. Of course, you have some color, which can take one of 3 values, create some bindings for them, and you try to compare if those C's are the same. To have it work, you need to have your type implement the EQ type class, which defines 2 operators, equals and not equals, and provides default implementations for those. So when you implement them, you can provide any for it to work. And this is pretty much how it works in Rust. This is the same code translated to Rust. You have an enum, which can have can take one of three values, red, green, blue. You create variables, you compare them. And again, to have it, to be able to do the operation, you need to implement a trait called, surprisingly enough, EQ, which provides the functions which have default implementations. This is not the real EQ class from Rust. It is a little more complicated, but this works exactly the same as in Rust, and it can be done in Rust. And traits are used to do all those funny things, oh, sorry. You might want to implement this, but this is silly. Nobody would do that for this simple thing. So you can have it automatically derived. This is what compiler does for you. You know how to deal with EQ and derives it for you. So Rust uses traits as very important part of the language. It uses equality with defined two traits, partial equality and equality, ordering, comparing two values to produce an order, also is done with traits. Clone and copy. Clone, they do basically the same, but the distinction between them is the cost. Copy is derived automatically for you if the type is simple enough, and it's always used implicitly. You never use, it doesn't provide any methods, actually. You can't call the method from copy. And for example, integer types have copy implemented. So you can just copy integers everywhere. It's considered a cheap operation. Clone, on the other hand, does the same, but it's considered expensive. So when you implement clone for your type, you need to explicitly call the clone method, and it's considered expensive. Operator overloading is done with traits. Add, assign, sub-assign, and so on, a couple of dozens of them. Iterating over types is also implemented in terms of a trait, iterator trait. Having an object that is callable as all traits, actually 3 traits, because Rust controls mutability. Looking into an object, indexing into an object, again a trait. Default trait, which basically tells compiler how to produce a default value for a type, like 0 for integers or something like that. Drop is used to control what happens when your value goes out of scope and the memory gets freed. So you can implement this trait to have some extra behavior at this moment. Sentencing, those two are interesting because they're used in threads. Sent items, those items can be transferred between threads safely. So they disappear from one thread, and the thread cannot reference them anymore, and they appear in another thread, and you can use them there. Sync items, the types values of the types that implement sync trait can be shared between threads. All the threads in the program can now use them. This is how. This is one of the ways that makes Rust thread safe, really thread safe. And starting with Rust 1.15, which was released two weeks ago, I think, you can do custom derives. Usually, compilers know how to derive those common traits like EQ, add, and so on. You can write some procedural macros to implement any of the traits you desire. This is a little advanced Rust, black box, black magic Rust, and I'm not going to this, but this is a very nice feature that they used in a couple of projects actually, like Diesel, which is ORM in Rust, or a serializer library. Which brings me to macros. Hardly any language has real macros. This is considered esoteric stuff, this is considered dangerous, people shouldn't use it, but it turns out to be very useful. And not like macros like in C, which is just string manipulation, but real hygienic macros. Rust has a couple of them. VEC, all macros need to end with a exclamation point. This is how you mark this is macro. This is what compiler expects. VEC provides a nice syntax to create list literals. Try is meant for handling errors. Panic, abort your program. Print, well, prints things. But also, macros allow you to build pieces of syntax that Rust doesn't support out of the box. And I used it as an example to build a functional composition with macros. Rust doesn't support composition of functions out of the box, but we can do it. Let's say we have something like that. We have a list of numbers, a vector of numbers, and we try to map over it with some more or less trivial example, but something more than a single function. And we can use that, but the only thing I care about in those yellow lines is the ABS function and the negative function. The rest is just ceremony, it's just syntax, and I don't really like it. I would like not to use it anymore, ever. So let's write a macro. This is a syntax to create macros. It looks a lot like a function. There's a thing on the left that defines a pattern that the compiler will look for, and the thing on the right after the double arrow that says it will be replaced with this. So in this case, we've got two identifiers, $f and $g, separated with a dot. And this will be translated into a closure, a function, closure, which takes an argument and applies those two in order. This is how we use it. Notice that I didn't use the exclamation point in the definition of macros, but I need to use it when I call the macro. This is how Rust works. I just used negative and absolute and just try to apply it. And of course, Rust provides you with a method to expand the macro to see what it actually sees, what it can understand. And sure enough, this is what we expected. This macro has problems. Like, it only allows applying methods, not functions. It only allows applying two methods, not any number of them, which is pretty limiting. Like, if I want to apply a function like that, let's write another macro. Let's call it C, like compose. And this is very basic stuff. You apply those functions in order. That's the like mathematical definition of composing functions. Do it like that, and sure enough, it expands to something we expected. The I32::ABS is a so-called universal function call syntax. This is a way, Rust provides a way to uniformly call functions and methods and all other things that can be callable, so that we can unify it and use it in contexts like this. And this means we can rewrite our previous example with this new macro. Notice that ABS is a function from the type, and neg, nec, is a function from the trait, hence the difference in casing. All right, so let's try now to define a function that applies three functions. You can be tempted to do this like this. Just apply them in order, but this is road to nowhere, right? This only works for 3 functions, but you will immediately have a case of 4 functions and 5 functions, etc. And Rust provides macros that are really recursive. So you can try to implement this in a smarter way to allow any number of functions. And that's it. The first line is, as before, when we have to have 2 functions, we know what to do. We have more, and this is this weird syntax of age expression, which is repeated with plus of 1 or more times, and the comma before that just says separated with commas. And this should return a closure that takes a result of recursive application of parameters and applies to its parameters and to the first function of the arguments. This is how we use it. Just use it like you'd expect. Just list all those functions. And sure enough, compiler responded to what we expect. The blue things, the first function from the list is applied to the result of calling the green function to the purple argument. And the green function is application of this macro for two functions. And we can go crazy. Now we can go crazy. With this macro, we can do anything we want. This is taking a list of numbers, filtering to get the first things absolute values of those numbers, then we negate them, then we count ones in binary representation, then we cast it to signed integer because count ones returns an unsigned integer, and then we apply an even function. And sure enough, we can see what it expands to, and this is some horrible code which creates closures, applies them, creates them, applies them. It's not something a human would write, right? It's not something a human would write. So maybe we're losing something. Maybe we should just forget it all and, like any normal human Java programmer, write it ourselves and forget those closure compositions. So I've created a benchmark. Rust, being a language that is focused on performance, has a built-in benchmarking facilities. So I created two tests to benchmark handcrafted code on the bottom and the macro on top. And they are pretty much the same in terms of performance. Rust compiler can see those all creation of closures and application is only temporary, and we will just optimize it out and pretty much produce the same code in both cases. So yeah, you can implement all those nice features like functional composition, use it anywhere. You go back, you can see that there are methods, there are trace methods, there are functions, there are even closures defined on the spot, so you can use it with anything, and you're not paying for it. Then this is pretty much all I had. Rust is a function that provides first-class functions, a language that provides first-class functions, which are pure enough for practical applications. That language that provides algebraic data types. We can do all nasty things with that. We have traits which work pretty much the same as type classes. And you can use macros to create all those things that are missing from the language. And you don't pay for it. I mean, you still got a C-level performance, or even better than C, because, well, types can enable very nice optimizations. Questions?
You've shown in your example of macros how you are making a macro working over identifiers. But is it possible to make, for example, macro which could be applied for type definitions? For example, I have macro that takes type definition as a parameter, so I can, for example, iterate over its fields or something like that.
Yes. There are, if you look into the definition of those macros, let me go back. You see there are the F, G, and H are suffixed with colon expr. This expression In the first macro, we used ident, which is identifier, and Rust provides many more of those, and types is one of them. It's ty, I think, if I remember correctly, which would make the compiler expect a type passed to the macro. However, it's not that easy as it is here. These are called simple macros, and they just replacing some code with some code. To iterate over like types fields or enums fields, you will need to write so-called procedural macro. It can be done, and starting from Rust 1.15, it's unstable, so you can rely that it's working. But you basically need to write a function that is called at compile time, which takes an abstract syntax tree as an argument, and then you can do anything.
Any other questions? Okay, if there are no more questions, then thank you.
Thank you.